Yes. Okay, so I'm going to discuss with you a hypothesis that we've been promoting, and at the beginning might sound a little bit out of place, but I think there are nice connections to be made between our what happens in visual perception and visual cognition in the brain and the way we perceive the environment around us. And this hypothesis states that, in simpler words than what you see there, is that we act, we believe, we perceive what's available to our brain and eyes and brain very early on. And early on I talk about hundreds, tens of milliseconds. And this determines our first impressions and determines our interactions very long into our interaction. So basically, my lab studies visual cognition and how is it that we, okay, I'll have to have different remotes for different things. So this mine will be for the pointer. Okay, so we study how is it that the brain recognizes objects, environments, and how is it that we interact with these objects, navigate around them, and so forth. And during the course of our research over the last decade or two, we kind of abolished a couple of myths that are studied in how the brain, in studying how the brain understands vision. So one of them is that we think, or we used to think, that what the brain does when it encounters a new visual object is it asks, what is this? And the slight, maybe it looks slight change that we've been promoting is that really the brain asks, what is this like? What is this that is in front of us, reminding us in memory? And we're not doing it consciously, but we're just creating this analogy between something new and something old in memory. Okay, and I'll just give you a quick informal two examples. When you look at this object that you've never seen before, unless you've seen me give this talk, it's not a very popular item. And I think all of you will have no problem understanding exactly that this is a high chair, right? So that's pretty amazing if you pause for a second and think about what your brain just did, looking at a collection of pixels that you've never seen before and know what it is, okay? And even if I ask you a more tricky question, what is this collection of pixels that really hardly has any clear shape here? And all of you will understand the function of this, right? So you know what it is, right? You all know what it is, yes? And when we encounter this guy in a party, we've never seen him before, even before he opens his mouth, we have a set of attributes, a set of beliefs about what is he like, what does he like, what does he do, how affluent it is. Our brain has the arrogance, if you will, of jumping into conclusions before accumulating more data, just by the fact that we connect what we see with what we know. Okay, so when we encounter a new item, we connect it to something in memory because we've accumulated so many things over the course of our experience. And the moment we gain access to, the moment we make this analogy between the new and the familiar, we gain access to all these associations that we've gathered over our lifetime. So I'll be talking about little stages of this and basically won't get into details of experimental designs, but give you a flavor of how we do our research and how these things we believe work in the brain. So in the first study that I'll show you here, we just asked what is this, what happens in the brain when we say aha. Speaking of conscious, here is the conscious brain and not necessarily the conscious cities, but how is it that we understand what happens in the brain when we look at objects very briefly? We present, you see the aesthetics? You see pictures presented very briefly, and you present before and after what we call visual mask, just to really limit the time that people have to look at the picture and see what happens when they say aha, when they are able to recognize the object. I'm going to show you a couple of brains here, and just so you are accustomed to the presentation, this is a real right hemisphere of a brain, right? This is not our subject, this is from an anatomy book, and you see here a right hemisphere of the brain seen from the bottom. Okay, so this is called the temporal lobe, this is the frontal lobe, and what we do is when we scan these subjects, we create a 3D model of their brain. I have one of these of mine printed in my office, and then we inflate them because the brain has gyri and sulci, and we do care about the surface, what happens inside the sulci. So we inflate them like we inflate a ball. And what you see here, this used to be inside. This used to be a sulcus, right? And now we look at the brain. So this is exactly, that's again, these are the temporal lobes. Your ears are like here. This is your forehead, okay, prefrontal cortex. So when we look at what happens in the brain when people recognize objects, you see these little dots here. They signify or they indicate cortical activation. It's not completely accurate, but take them as where the brain is active when we recognize objects. And I'm not assuming this is really important for you or for anybody really, that the exact locations, but it's interesting for us in order to develop understanding of the mechanisms that underlie visual understanding. So we found these areas that recognize, that are active for recognition, which is not surprising because it falls in areas of the brain that are called the visual cortex. So you would expect that the brain would recognize visual objects in the visual cortex. But what really interested us is this prefrontal activation. So the prefrontal cortex is taken sometimes to be the CEO of the brain, taking high-level executive decisions. And in that sense, it's not supposed to be bothered with low-level perceptual decisions. And here we find this high-level area active in low-level visual recognition. And we ask ourselves why. So there's the traditional view of how the brain works when we recognize objects, and the traditional view is very hierarchical. We start from the primary visual cortex. So visual information radiates from your eyes, the retinas, and almost directly to the primary visual cortex here. And there's a hierarchy of propagation of analysis of the visual information from little lines and spatial frequencies and colors and contrast, and it propagates increasingly more complex until it reaches an area where we say, aha. You can say that this is the first activation I showed you. And only then, that's a traditional old school view of how these things work. Once we recognize the object, this is projected forward to the prefrontal cortex. You're the CEO. I'll just tell you that this is an umbrella. Go do with the umbrella whatever you think is important. So that's the old school. What we suggested was, because we found this prefrontal activation in recognition activity, we thought, maybe this actually high-level area helps recognition. It's not just waiting there. In other talks, we talk about the brain as the proactive brain, in the sense that it's not reactive. It's not just sitting there waiting to be activated, but constantly generating predictions about what might happen. Okay? We have all this amazing machinery. Why just sit there until it's being activated? So our alternative interpretation or alternative hypothesis was maybe the brain generates predictions very quickly, aided by this area, and how it might do that. There's something in the visual environment that we call, it's a technical term you might have heard of, but if not, I don't think it's a big deal. There's spatial frequencies, just like there's time frequencies, right, of audio sounds and others. There's also spatial frequencies, meaning how quickly information changes, visual information changes. So in the extreme, there's the low spatial frequencies. You take the intact image and you just filter it, so to speak, here to show you only the low spatial frequencies. And you see that these are the low changes, the slow changes in space. And you see that low spatial frequencies convey global properties. Okay? They convey aspect ratios, they convey general orientations, global blobbiness, whereas the high spatial frequencies convey the details, fine details. Okay? All of this exists in your visual environment. If I take this picture now and I filter it, I can filter it to different band passes and find that there's different information conveyed by different frequency bands. What's interesting is this type of information, we call it sometimes global. This is global and this is local information. So the global information is like the trees and the forest, right? So the forest, the global information, is extracted by the brain significantly faster. So we first understand the global properties, and again, we're not conscious of it. We just see the picture as it is. We see the image as it is. But in the brain, this type of information is extracted and propagated and analyzed faster. So we get the general gist of a visual scene before we understand the details. Okay? And this has all we can make up stories about evolutionary psychology, why this might be, but generally we see that this is both with physiology and with psychophysics and all these nice experiments, we find that the brain indeed extracts this information faster. And this is very useful. It seems blurry, and it's like, why would the brain need such information? So again, let me give you just two quick informal demonstrations. So I think these are two filtered objects, low spatial frequency images. They only convey the low spatial frequencies, this information that's extracted faster. So if I ask you what this is, I'm sure that you know what it is. If I ask you to guess, can you guys guess what you see here?
Drill.
A what?
A drill.
A drill. Good. You saw my papers, huh? Just kidding. Good, good. Anybody else?
Hair dryer.
Hair dryer. Okay. So you see that this is indeed could be interpreted either as a hair dryer and a drill, or a gun, and sometimes I get a couple of other interpretations. But basically, what happens here is that you look at something very, very rudimentary. There's hardly information here, but we could already limit the amount of possible interpretations significantly. So instead of the brain considering tens of thousands of objects that we're familiar with, now you narrow down 3 minutes. You're kidding me. No, we only started. Okay, so let me rush through this because there is some stuff related to architecture here. Anyway, so we found that the brain is really working fast in generating predictions based on low-level information. And then we realized that individual objects are not enough. Objects in our environment appear in scenes, right? That's how we see objects, embedded in scenes. And what's interesting is that these scenes have typical arrangements very often, right? There's nothing unusual about this scene that I'm just looking at, or that you're looking at. There's nothing unusual. People sitting, and that's how I used to see it. People on chairs and not chairs on people, right? And you're on the floor, and the projector is at the top, and the walls are on the sides, and the clock is on the wall there. So we call this, in technical terms, statistical irregularities. Things happen together in our world, right? And the brain picks up these statistical irregularities. We are used to the fact that the refrigerators are usually in kitchens. Maybe not all the time, so there's some probability, but kitchens contain refrigerators. We know that when we enter a kitchen, we can generate predictions about what to expect there, or what to expect in a conference room, or in a bedroom, or in a gymnastic new room that we'll all have in our houses now. So how does the brain picks up this information? I won't get into details here, but you see again that with low spatial frequency, we get the gist of a scene, and we can understand that this is a car. Look at how little information there is, but you already know a lot. You don't know what type of car it is, right? But you know that there is a car there. So with very little information, you already gain what you need. We call it basic level information. And the same object can be assigned, there's something exactly here, but the same object can be assigned different meaning depending on its environment. Okay, so we found this network of areas that are activated when people look at what we call contextual associations, these things that appear together. And of course, you don't need to memorize these names. But something interesting is about this area, parahippocampal area, that Hugo is very familiar with. And just like you, when I saw these results, I had to look in an anatomy book. It's like, what is this name? What is this associated with? And I read a little bit, and I realized that there's an interesting phenomenon happening in this area in the literature. So all these dots that you see here are different studies, okay? And people find activation, and they are coordinates, and they say, here is where where people analyze X, okay? And what you see here is green dots are studies that looked at spatial understanding, navigation, houses, coordinates, maps. That's where people what is activated. And when people study episodic memory, associations, context, we find these red dots. And it's the same area that seems to be activating or seems to be mediating both spatial navigation and contextual associations or episodic memory that is highly associative. And what we suggest is contextual associations really bridge both, that spatial maps, that spatial organization actually relies on associations at its basis. And I'm a little bit out of tune here because this 1 minute left freaks me out. So let me just skip. We did this also with how people understand faces and first impressions of faces, and we found that people are extremely fast. 39 milliseconds are enough for us to say if somebody is trustworthy or not. And we found that this information is being conveyed again by the low spatial information. So low spatial frequencies are not only propagated faster, they taint, they flavor our perception of our environment. We did the same thing also with objects. We had this hypothesis that people would prefer curved objects compared with sharp objects. So we took everyday object and we just used a curved version and a sharp version. The sharp version, just everyday objects with no emotional valence to it. And we looked at whether people would indeed prefer the more curved objects compared with the sharp objects. And we found that indeed that people like the curved objects significantly more than they like sharp objects. Now, I let just name drop for a second. I know that Frank Gehry didn't like this result. He trashed us in one talk in a nice way, but still, it made me understand I need to emphasize that we're not claiming that what determines preferences in contour is just whether it's smooth or sharp. This is only one element, but there is some inherent preference of people to like more the smooth versus the sharp objects. And again, we found that this is conveyed by the low spatial frequency and not the high spatial frequency. These results were taken forward by a friend, by now a friend and a collaborator architect in the Technion, Yasha Groban, who took these ideas and created in virtual reality sharp versus smooth spaces. And the idea there was whether people would feel differently in sharp cornered rooms versus smooth rooms. And indeed, we found that they replicated the same result, but with people interacting with this virtual environment rooms. And we did all these measurements like you saw before. There's a very basic EEG. And we found that we could distinguish between activity in the brain when people are inside a smooth versus a sharp object room. And yeah, we won't get into the details, but you can differentiate when people are in different, which makes sense. You're in different space, you feel differently, but here we try to control for all elements and just leave different this parameter of smoothness of the corners versus edginess. I just realized during the other talks that we have another study that I'm not going to mention here, but I'll tell you briefly, and you can ask me later, where we showed much earlier, this was when I was still in the US, study that asked what would, diabetes is a big deal, especially in the US now, and what would be design elements of streetscapes that will promote people walking rather than taking their car. So you have half a mile to go to the next donut store. Do you take their car or do you walk there? Anyway, so I'll finish here by saying that perception relies on existing knowledge as much as it does on incoming information. So the way we see our environment, it's a mistake to think that it emanates just from the fact that, it's a result only of what's coming through our eyes. It's really a result of how our memory and our experience connect with what we see. And very often it affects our interpretation of the environment, where we're coming from, our state, our history, etc. And by rapidly answering what is this like, our proactive brain generates predictions that facilitate perception, cognition, affect, and action. And I told you about this lasting primacy hypothesis, where we really rely on what is available in the picture early on to kind of influence our interactions and perceptions. And the different generations of lab members that helped. Somebody cleaned up my slides, I think. It wasn't arranged like this. But thank you very much.